Welcome to AI Paper Slop. We are jumping right into a brand new paper today titled HumanCLAW: Can Vision Language Models Act Through a Body?
Yeah, this one is a joint release from Meta, the University of Washington, and NTU, just published on August 5th, 2026.
Right, and if you are building, training, or deploying embodied AI, I'm going to give you the core insight of this paper right now in the first minute.
You really need to hear this.
Yeah, so when you take a state-of-the-art vision language model, a VLM, and you drop it into a physical humanoid body, it fails miserably.
Completely falls apart.
We were talking about a maximum 16.8% success rate on a dead simple task, literally just finding an object and sitting on it.
Which sounds bad, but the real reason you need to pay attention to this research isn't just the failure itself.
Exactly. It is the diagnosis of why they fail. The researchers definitively proved it is not a perception bottleneck, right?
Right, they can see just fine.
And it is not low-level motor clumsiness either. The fundamental flaw is that current VLMs lack what the authors call embodied self-awareness.
They operate like ghosts possessing a machine.
Yes, they can perfectly recognize a sofa in their field of view, but they literally forget they have arms and legs.
It's wild. They just constantly crash their limbs into furniture because they have absolutely no intrinsic sense of their own physical volume.
So the implications of that failure mode are just massive for how we train these models going forward.
Oh, totally. I mean, we have spent years optimizing these architectures to perfectly describe a static room.
And they do that brilliantly, right?
They do.
Yeah.
But the moment you give that intelligence a physical shell with dimensions, weight, and spatial consequences, the high-level reasoning just shatters.
The model is essentially operating as a disembodied eyeball floating through space.
Exactly, just a floating eyeball.
So, to understand how the researchers isolated this specific ghost flaw and how they proved it wasn't just a vision glitch, we first have to look at the historical nightmare that is evaluating robotics in the real world.
Right, because for years, there has been this massive confounding variable in embodied AI research.
The entanglement of decision-making and low-level motor control.
The classic evaluation gap. I mean, think about it. If you put a physical humanoid robot in a room and tell it to walk up a flight of stairs, and it takes 3 steps, loses its balance, and falls backward.
Right. How do you, as an ML engineer, debug that failure?
Exactly. You have a massive stack trace of potential issues. Did the VLM issue a geometrically flawed command, like telling the leg to step 20 centimeters too high?
Or was the semantic command flawless, but the low-level PID controller just failed?
Yeah, maybe a deer slipped, or the foot actuator just couldn't handle the friction of the stair tread.
It's like testing the strategic brilliance of a chess grandmaster by forcing them to play the game using a malfunctioning arcade claw machine.
Oh, that's a great analogy.
Right. If they dropped the knight on the wrong square, you have no idea if they had a terrible strategy and chose the wrong move, or if their strategy was brilliant, but they just fumbled the greasy joystick.
You cannot accurately grade the brain if the hand is broken.
And in real robotics, that greasy joystick is constantly drifting due to motor heat, sensor latency, joint wear, all of that.
Yeah, that hardware noise completely masks the actual cognitive capabilities of the model. But HumanCLAW completely bypasses that hardware stack.
Because it's a framework designed to decouple the high-level action decision-making from the low-level motor execution.
Right. The VLM acts inside a highly realistic physical simulator. The environment strictly accounts for gravity, rigid body collisions, real physical consequences.
But crucially, it completely factors out balance issues and motor tracking errors.
So they essentially fixed the joystick.
Exactly. If the Grandmaster decides to move the knight to e4, the knight goes to e4 flawlessly, every single time.
Yes. In the HumanCLAW framework, if the agent commands a step forward, that step executes perfectly according to established kinematic rules.
Therefore, if the agent falls over or gets its leg trapped behind a table, we know with absolute certainty it wasn't a classy motor glitch.
Or a slipping gear, yeah.
It was a semantic failure. It was a failure of the VLM's spatial intelligence and action planning.
We are finally able to isolate and grade just the brain.
Okay, so since we have this frictionless semantic to kinematic bridge, let's talk about how the VLM actually controls this virtual body.
It's a really tight loop.
Right. We're looking at a sub-second loop here. The framework is running at 30 frames per second.
And at each step, the VLM takes in an egocentric RGB image Basically, the direct camera feed from the robot's face.
Along with a text history of its recent actions, right?
Exactly. And from that data, it outputs one atomic skill.
And by atomic, the paper means basic granular commands, like walk, turn, or sit.
Combined with continuous parameters, like turning a specific number of degrees or sitting at a specific height.
And that granular control is routed through what they call a motion-based DIT diffusion transformer.
Right.
But wait, before we get to the diffusion model, I have to challenge the premise of using atomic skills in the first place.
Okay, go for it.
We are testing massively powerful frontier models here, right? Architectures with billions of parameters. Why are we handicapping them with granular commands like walk 0.3 meters at a 15-degree angle?
I see where you're going.
Why not just give the VLM a macro command, like sit on the sofa and let its immense reasoning capabilities figure out the rest?
Well, because providing a macro command completely defeats the purpose of evaluating spatial intelligence.
How so?
If you give a system a sit-on-sofa button, you are effectively outsourcing all the moment-to-moment geometric reasoning to a pre-programmed script.
Oh, I see.
Think about the actual physics of sitting down. You have to locate the target, map a collision-free path to it, approach it, stop at the precise distance where your shins aren't hitting the frame,
Turn your body 180 degrees so your back is to the seat.
align your center of mass, and then lower yourself. A macro command hides all of that complexity.
Right, okay.
By restricting the vocabulary to atomic skills, the framework forces the VLM to handle the step-by-step spatial reasoning itself.
It strips away the training wheels.
Exactly. It exposes the model's naked action intelligence.
Okay, that clarifies things. If we hide the geometry behind a macro script, we aren't testing the VLM, we are just testing the script.
That's a thought on.
So back to the execution layer. The VLM outputs this specific continuous atomic command. How does this system translate a text token like walk 0.5 meters into the fluid movement of a humanoid body with dozens of joints?
That is where the motion-based DIT comes into play. It is a surprisingly compact 38 million parameter, 10-layer diffusion transformer.
38 million is tiny for a model these days.
Right. But instead of denoising pixels to create an image, it denoises a sequence of poses to create fluid kinematics.
Well, that's clever.
Yeah, it takes the last 5 clean history frames of the body's posture as its condition, and it predicts a 15-frame future motion chunk.
And at 30 frames per second, that translates to exactly 0.5 seconds of continuous, realistic physical action.
But here's the thing. Diffusion models, especially base ones, just generate natural-looking data based on their training distribution.
Right. If the base DIT just knows how a human body naturally moves what we would call a kinematic prior, how do they force it to obey the specific parameters of the VLM's command?
They use this brilliant mechanism borrowed from image generation. They use plug-and-play skills that function very much like control net adapters.
Oh, wow.
Yeah, so the base DIT is frozen. It holds the pure kinematic prior of natural human movement, so the joints don't, bend backward or break physics.
And the adapters.
The adapters are small, specialized networks trained for specific skills, like walking or turning. When the VLM issues a command, the framework dynamically snaps the corresponding adapter onto the frozen base model.
That's incredibly modular.
It is. This guides the diffusion process, aligning that natural motion prior with the exact degree or distance the VLM requested, without having to retrain the entire 38 million parameter model for every new skill.
The architecture is elegant, but it brings up a massive red flag regarding the nature of VLMs.
The hallucination problem.
Exactly. These models are notorious for hallucinating. They hallucinate facts, they hallucinate code, and they hallucinate logic.
Oh yeah, constantly.
Now, you are asking an autoregressive text model to do continuous, sub-second, step-by-step spatial reasoning in a dense 3D environment.
That sounds risky.
It sounds like a recipe for the model confidently deciding to walk straight through a solid wall because it mathematically hallucinated an open doorway.
Yeah, you would think so.
So how does HumanCLAW prevent the VLM from just completely detaching from physical reality?
Well, the authors anticipated that exact problem. To tether the VLM to reality, they implemented a strict reasoning scaffold and a critical safety layer called the Verifier.
Okay, break that down for us.
The VLM is not permitted to just spit out a movement token. It is forced to follow a progressive high to mid to low logic chain. First, it must output a highly formatted visual state. It has to explicitly generate text detailing what objects it currently sees, its estimated distances to those objects, and the presence of any immediate obstacles.
So it's essentially forced to write out its own depth map and semantic segmentation before it can make a decision.
Exactly. It has to show its work.
I love that. And the second step?
The second step builds on that. Based purely on that generated visual state, the VLM must state a mid-level plan.
Like a short-term goal?
Yeah, a textual objective that remains valid for the next 2 to 3 seconds. It might output, navigate around the left side of the coffee table to reach the open floor space.
Okay, thank you, sis.
Only after generating the visual state and the mid-level plan is it finally allowed to select the low-level 0.5-second atomic motion skill.
But even with a scaffold, the model's internal logic could still be flawed, right?
True.
Like, it could correctly identify a wall 0.2 meters away in its visual state and still confidently output a low-level command to walk forward 0.5 meters.
Which brings us to the skill-specific spatial response verifier. This is the ultimate reality check.
How does it work?
Before that 0.5-second motion chunk is actually sent to the simulator's physics engine to be executed, this short context verifier intercepts the command.
Oh, so it checks the VLM spatial math.
Yes, it runs a rapid geometric check to see if the VLM is hallucinating progress or violating physical rules.
So if the VLM proposes a sit command, but the verifier's deterministic check sees the chair is still 2 meters away, it blocks the action.
Exactly. Or if the model tries to step forward into a solid object, the verifier intercepts it, rejects the physically impossible action, and forces a replacement behavior, usually just stopping or reevaluating.
Wow.
And the ablation studies in this paper prove just how much these models hallucinate space. When the researchers disabled this verifier, navigation success across the board collapsed from 27% down to an abysmal 2%.
Wait, 2%?
Yes. 2%. Let that sink in. Without a deterministic heuristic constantly checking their math, state-of-the-art VLMs will confidently walk into walls or try to sit on thin air 98% of the time.
That is genuinely terrifying.
The verifier is the only thing keeping the loop closed and functional.
So we have this theoretically perfect evaluation framework. We have completely factored out hardware noise and motor clumsiness.
Yeah.
We have a strict reasoning scaffold forcing the model to show its work. And we have a deterministic verifier acting as a safety net against spatial hallucinations.
All the crutches are in place.
Right. With all of these safety nets, how do the heaviest weights in the AI industry actually perform?
The results are staggering, and not in a good way.
Lay it on me.
The researchers developed HumanCLAW-Bench. It's a rigorous testing ground consisting of 1,218 long-horizon egocentric episodes spread across 41 highly varied, complex indoor scenes.
And the goal is simple, right?
Very simple. Find a specific target object in the house, navigate your body to it, and successfully interact with it by sitting down.
Okay.
They ran 9 frontier models through this gauntlet, including the absolute bleeding edge of the industry, GPT 5.5, Gemini 3.1, Gemma 431B, and Qwen.
These are the models passing the bar exam and writing production-level code.
And they fall apart in a simple virtual living room.
Ouch.
The highest performing model across the entire benchmark was Gemini 3.1. Its absolute ceiling for success was 16.8%.
16.8% success on a task a toddler could do without thinking.
And that is the best case scenario. 4 of the 9 frontier models successfully sat on the target in 0.2% of episodes or less.
It is a complete architectural bloodbath.
The researchers actually map out this performance drop in what they call the funnel of failure.
Funnel of failure, I like that.
Yeah, so the task has 3 distinct stages, and the models hemorrhage success at every single one. Finding the target somewhere in the house, they manage that roughly 32 to 64% of the time.
Okay, not great, but manageable.
Navigating through the room to the target, once they spot it, success plummets to between 0.8 and 42%.
Oh, wow. Huge drop.
And the final stage, the actual physical interaction of turning, aligning, and sitting, almost completely wipes out whatever success rate was left.
You know, if you are an ML engineer listening to those numbers, your immediate instinct is probably to blame the vision encoder.
Oh, absolutely.
Right. You take a model trained on perfectly framed, high-resolution 2D web images, and you drop it into a cluttered, complex 3D rendering of a bedroom, asking it to find a specific wooden stool partially obscured by a bed.
It seems like a vision problem.
The logical assumption is that the egocentric camera feed is just too noisy, and the VLM simply cannot perceive the target.
It is the most logical assumption, but the data in the paper proves it is entirely wrong.
Wait, really?
Yeah, perception in this context is practically a solved problem. The researchers measured this meticulously using two distinct metrics, GeoFinds SR and Finds SR.
Okay, so GeoFind SR is the geometric ground truth. It triggers when the target object is mathematically rendered in the robot's egocentric camera view at a legible size.
Right. The paper specifies over 100 pixels.
The pixels are objectively on the screen, but Find SR is checking if the VLM actually acknowledges those pixels in its generated reasoning text.
Exactly. Find SR measures whether the VLM explicitly outputs, I see the wooden stool.
So if perception was the bottleneck, we would see a massive gap between those two numbers.
Right. The object would be on the screen, but the VLM wouldn't recognize it. But that gap doesn't exist.
No way.
Across the top models, the difference between GeoFind SR and Find SR is only 5 to 10 percentage points.
That's a nothing.
If the object appears in the camera feed, the vision encoder processes it, and the VLM semantically recognizes it. They can see the target perfectly well. Perception is not why they fail.
Which brings us to the core revelation of the paper, finding 6.
Oh.
If they can see the target, why can't they reach it?
This is the crazy part.
The answer lies in what happens to the rest of their body while they stare at that target. The ghost in the shell problem.
No current VLM possesses the architecture to perceive its own physical body.
This is the most fascinating and bizarre behavior documented in the research.
I know, it's wild.
The team tracked collision statistics across all the models during navigation, and a definitive, undeniable pattern emerged. The robot's legs and feet violently collide with the environment in 28 to 45% of all steps taken.
And the arms and hands smash into obstacles 20 to 35% of the time?
But the head, the camera housing.
The head collides with the environment in under 7% of steps.
It is exactly like driving a massive semi-truck, but your only viewpoint is a tiny, narrow windshield at the very front of the cab.
That's a perfect way to picture it.
You are meticulously, obsessively steering to make sure your front bumper doesn't scrape a stop sign. But because that's all you can see, you have completely forgotten you have a 50-foot trailer attached behind you.
You are just violently sideswiping parked cars and knocking down light poles every time you turn a corner.
Completely oblivious to the destruction because it's not dead center in the windshield.
Right. The VLM only optimizes for the pixels directly in front of the camera. It treats its own peripheral body parts, its physical volume, as if they do not exist.
Because fundamentally, in the token space, they don't exist.
Exactly.
These models are trained on billions of parameters of internet text and disembodied visual question answering. They hold absolutely no instinctive internal mathematical model of which pixels in their peripheral vision belong to their own limbs.
Nor do they possess the architecture to infer where those limbs are in 3D space when they leave the camera frame.
The model issues a command to walk forward because the center of the screen looks clear, entirely unaware that its left knee is currently jammed against a dense mahogany coffee table.
It is a brilliant, highly articulate mind, completely devoid of a somatosensory system.
So, how do we solve it?
That's the million-dollar question.
The standard ML reflex to any missing information is to just feed the model more data, right?
Usually, yeah.
If the agent doesn't know where its body is in space at this exact second, we just pump up the context window. Give it a longer visual history, say, the last 10 frames of egocentric video so it can track its own velocity and infer its physical volume over time.
Well, the researchers tested that exact hypothesis, and they uncovered a highly counterintuitive result. Pumping the context window with a long visual history actually degrades the agent's performance.
Wait, really?
Yeah. When they increased the visual history input to 10 frames, navigation success dropped sharply from 27% down to 13%.
Flooding the model with more spatial information actually cuts its success rate in half. Why?
Because the model's attention mechanism gets overwhelmed by visual noise. In a 3D environment running at 30 frames per second, 10 frames of video look almost identical.
Oh, because the background pixels barely shift.
Exactly. When you flood the context window with all those redundant frames, you dilute the signal of the current moment.
I see.
The attention heads end up allocating computational weight to the static background noise of where the agent was, and it loses track of the crucial, minute geometric deltas of exactly where it is right now.
The model becomes paralyzed by its own visual memory.
That's exactly it.
Okay, so a deep visual history is a trap. But earlier you mentioned the high to mid to low reasoning scaffold, specifically the mid-level textual plan.
Right.
If visual history dilutes the signal, what about the text history? Does holding on to a textual objective help?
Oh, the mid-level textual reasoning plan isn't just helpful, it is structurally vital.
Really?
The ablation studies showed that without that persistent text history, interaction success plummets to 0%.
Absolute
So
zero.
absolute zero. And the reason comes down to compositionality. Reaching a chair is a completely different cognitive task than interacting with a chair.
Right, you can't just forcefully walk your shins into a stool and claim you successfully sat on it.
Precisely. The act of sitting is a highly compositional, multi-step routine. You have to navigate to the target, recognize you have arrived, halt your forward momentum.
Initiate a sequence to turn your body 180 degrees so your camera is now facing away from the target.
Align your invisible legs with the invisible seat, and then execute the sit command.
That's a lot to keep track of.
It is a purely reactive, step-by-step policy, one that only looks at the current frame and guesses the best immediate next move, cannot possibly hold that complex sequence together.
Because once the camera turns away from the chair, a reactive policy forgets the chair exists and just wanders off.
Exactly. The mid-level textual objective acts as the cognitive glue. It allows the model to internally state, I cannot see the chair right now, but that is because I am currently in step 3, the turning around phase of my overarching sit objective.
It provides the object permanence required for physical interaction.
That is exactly what it is doing.
This research represents a massive paradigm shift for how the industry needs to think about evaluating and building embodied agents.
It really does.
We have spent the last half-decade obsessing over spatial understanding training models to perfectly identify objects, read labels, and map relationships in a 2D image.
And we got really good at it.
We did. But the HumanCLAW framework proves that all of that high-level spatial understanding is completely useless if the architecture cannot translate it into closed-loop embodied decisions.
Action intelligence isn't just about describing a room.
Right. It requires an online, persistent estimate of the physical consequences of your own body as it moves through that room.
It highlights a completely missing dimension of machine intelligence. We are trying to force a disembodied brain to drive a physical vehicle without giving it any dashboard sensors for its own wheels.
Until we solve the embodied self-awareness bottleneck, these models will remain trapped as incredibly articulate ghosts.
Very well put.
Which leaves us with a profound structural question for the future of AI. If vision language models are fundamentally built and trained on disembodied internet text and 2D images, a digital universe entirely devoid of physical consequence, friction, or gravity, will we ever achieve true action intelligence using this autoregressive token prediction architecture?
Or does the path forward require a radical architectural departure?
Exactly. Do we need to invent a synthetic somatosensory cortex for these models? A native mechanism to embed proprioception, the actual sensation of touch, of physical resistance, of unseen limbs existing and occupying volume in 3D space directly into the token space itself.
It is a massive architectural hurdle.
It is, and it's something for you to chew on as you design and train your next model. We'll do another deep dive into the material next time on AI Paper Slop.